Welcome to my presentation on the role of meaning in visual working memory. Real-world objects, but not simple features, benefit from deeper processing. Visual working memory is almost always studied using simple stimuli, while in the real world we encounter much more complex visual objects. And of course, there's very good reasons to use such simplified displays. For example, because we have a very good understanding of the representational structure of the stimuli and thus can build clear quantitative models of performance and capacity. But these simple stimuli differ in important ways from stimuli in the real world. For example, objects relate to prior knowledge and are visually more complex. And maybe not so surprisingly, these differences have important consequences for working memory capacity. In particular, we have previously shown that working memory capacity is higher for realistic and meaningful stimuli compared to simple stimuli. Today, we want to ask what it is that drives better memory performance for realistic relative to simple stimuli. And we will focus in particular on the limits at encoding, so whether processing of the items initially is the same or different. Why would this be the case? Simple color displays can be processed quickly and in parallel. And so really, even if I showed you a color display for a longer time, there's not much more you'd get out of it. And while a display with real-world objects can be processed in just the same way, it can also be processed in a fundamentally different way, namely deeply and semantically, when items are focally attended and processed individually. And so today I want to ask whether these differences in encoding can at least in part explain the real-world object benefit in working memory. To test this, we will use a standard visual working memory paradigm in which we ask participants to remember a set of items and after a short delay, cue them to a location and ask them which color they saw at that location using a two-alternative forced choice. So this looks something like this. We contrast these color displays with displays that use real-world objects. And in all the tasks that I'll be presenting today, we ask participants to remember 6 stimuli, use this 2AFC method, and we also have participants do simultaneous verbal suppression tasks to limit the ability to use verbal encoding or labeling strategies. To directly manipulate how the items are initially encoded, we either show these items all at once, promoting a parallel and holistic encoding strategy, or we show these items sequentially, which should push participants to focus on each item individually and thus process them in a deeper and more meaningful way. In our first experiment, what we find is that real-world objects are always remembered better than colors, regardless of encoding condition, replicating our previous work. But most interestingly, we find a qualitative difference between stimuli and encoding. The real-world object benefit is larger when items are shown sequentially relative to all at once, so individual one item at a time encoding helps memory for real-world objects. For colors, we find the opposite. Working memory performance is better when colors are presented simultaneously relative to sequentially, consistent with the idea that low-level features are processed efficiently in parallel. In a second experiment, we replicate these results across subjects, demonstrating that these effects are robust and also not driven by order effects. So again, we see a real-world object benefit across all conditions, and that this benefit is larger during sequential versus simultaneous encoding, even when simultaneous encoding is almost twice as long as sequential in this particular version of the experiment. Colors again show the opposite, benefiting mostly from simultaneous encoding. And so what this suggests is that sequential encoding allows participants to extract semantics and meaningfulness from the objects, which then drives the benefit in working memory performance. An alternative explanation might be that the difference in visual complexity actually underlies these effects, the idea being that there are more features told onto for real-world objects relative to these simple unidimensional colored circles. And while this idea is largely at odds with previous work showing worse memory for more complex items, we wanted to test this directly with regards to encoding limits. And so in the third experiment, we compared memory performance for realistic objects and scrambled versions of these objects, which maintained the physical complexity of the objects, but were unrecognizable and thus meaningless to the observer. What we found was that intact objects are again better remembered, replicating the real-world object benefit, and that this benefit is larger for sequential encoding. The scrambled objects look like colors. Overall performance is lower and memory is better for simultaneous than sequential encoding. So this suggests that individual sequential processing only benefits meaningful stimuli, but not complex, meaningless stimuli. So in sum, encoding limits appear to work in fundamentally different ways for realistic objects relative to simple stimuli. Simple features uniquely benefit from parallel encoding, while realistic objects benefit from the deep processing afforded by sequential presentation. Overall, these experiments suggest that results from simple features at high set sizes should not be generalized to real-world objects. Rather, it seems that standard visual working memory tasks, so many quickly flashed objects at encoding, are uniquely suited to simple features. And while we can encode real-world objects just as colored blobs, so the same way, we can also process meaningful objects more deeply and can improve memory for them. Most broadly, our results indicate that visual working memory does not appear fixed capacity. Adding meaningful dimensions, but not simple complexity alone, recruits more working memory capacity. The results that I presented today are in press, so you can read more about this in this paper here on the left. And I also want to point you to another preprint in which we show how important it is to match the foil difficulty in working memory tasks when comparing across different stimulus classes. Thanks for stopping by, and thanks for your attention.